Good day and welcome to Letters and Politics. I'm Mitch Jeserich. This is a quote: Universe or multiverse, designer or not? This was the fateful question that would keep us occupied for 20 years. One homework problem led to another, and soon Stephen and I found ourselves in the midst of what would become one of the most heated debates in theoretical physics in the first part of the 21st century. That's from the new book called On the Origin of Time, Stephen Hawking's Final Theory. It is written by Thomas Hertog, who is an internationally renowned cosmologist who for many years was a close collaborator to the late Stephen Hawking. He is a professor of theoretical physics at the University of Leuven, where he studies the quantum nature of the Big Bang. Thomas Hertog, it is a very good pleasure to welcome you to this program, sir.
Thank you. Pleasure to be here.
Stephen Hawking died in 2018. If he was still alive now, it's my understanding he would have been the co-author of this book. Is that accurate?
That is right. Sure. But of course, the reality is very different because, in fact, he asked me to write this book shortly before he died, realizing, of course, that he was nearing his final days, and realizing also that our research in the last couple of years really led to a new vision of the cosmos, which he thought should be the gospel he thought should be spread, and here we go.
We're gonna get into this new vision of the cosmos, but before we do, tell me a little more about your relationship with Stephen Hawking. You begin the book, The Origin of Time, by accounting how you first met him in 2002.
Right. In fact, in 1998 already. Right. I first met Hawking in his Cambridge office in the UK. It was kind of a job interview, really. He was debating on whether or not to take me on as his new PhD student. And so that was our first conversation. I walked in and there he was, and it was rather surreal, of course. He had already lost his voice by then, but he was talking through a computer voice. So what was on his mind then? In fact, these first few years, we spoke a lot. He could talk quite fluently, I would say, through his computer voice. And what I admire also is that, he was already a public icon by then. Brief History of Time had been published. It had sold, I don't know how many copies.
One of the best-selling books, science books ever.
Right. But at the same time, so this is the late 90s, 10 years later, he was grounded in research. And I've always admired him for that sort of, despite having these public spotlights on him, he remained so passionate about these fundamental cosmic questions. And so we got going. And I think we developed a kind of, in theoretical physics, you really have to develop a kind of language with your close collaborators, a sort of understanding, a sort of intuition, shared intuition, really. And that's what we built on for many, many years afterwards. Even when late in his life, the communication became very difficult, of course.
Yeah. And just the understanding of language and having shared understanding. So you don't have to begin at the beginning every time, because you're getting into obviously some pretty deep things.
Right. And towards the end, it was no option at all to begin at the beginning, because there were hardly any words which could be spoken.
And yet it is here at the beginning, in the way that you're able to communicate with him, where you're getting to some of the most profound and deepest thoughts I guess he would have towards the end here. I don't mean to rank his thoughts or anything, but I'm just saying this is some deep stuff you're getting into here with this final book on the origin of time.
Yeah, well, the stuff what was on his mind, late 90s in cosmology, what was going on? In the 90s were revolutionary in two ways in cosmology, the study of the universe, right? On the one hand, you had new observations of the far, far distant universe, and these observations were telling us that in the last, say, 4 or 5 billion years, the expansion of the universe had been speeding up. This was a real surprise. No one had any clue how to interpret this and what to think of this. And then the second thing, and deep down it's connected to the first one, the second thing was more sort of a theoretical discovery that, hey, wait a minute, maybe the Big Bang was not unique. Maybe there are many Big Bangs. Maybe there's a giant inflating space which harbors many kinds of different universes. That was the situation in the 90s. A theoretical discovery, a wild idea, maybe there's more than one universe, and an observational discovery that, hey, there's something special about the expansion of our universe. And Stephen was uneasy about both discoveries. He felt that this whole idea of many universes wasn't quite proper science. And the reason he felt so was not just because obviously we cannot go to another universe and check it out. No, it was a more fundamental problem, which has to do with the fact that if you have many, many universes in your theory, then, well, which one should be our universe? What do we predict? What does the theory predict that we should observe? That which kind of universe we should be living in? And that's a real paradox. When you start talking about many universes, you're lost in that. And I think Hawking was one of the first cosmologists to realize, hey, there are serious problems associated with the idea of more than one universe. How should we think about this? We're missing something. And that was the first conversation. So yeah, pretty deep stuff. I was confused.
Well, it's a big deal too, because Thomas Hertog, we are living in a moment in which there's a whole movie industry about the multi-universe at the moment.
I do realize this. Yes. I get confused by these movies too. Yes.
It is so. This is one of the arguments that you make that it's not a multi-universe. Is this largely accepted in cosmology now in the physical world, or is it still a vigorous debate?
That's a good question. So now we are 20 years later, 25 years later. What happened with the multiverse? Two things, I think. This question that we were just talking about, like sort of a paradox, like if there are many universes, where are we? It's a kind of breakdown of science. I think it's generally recognized in the scientific community now that this is a serious problem, that it's almost like that the theory of the multiverse is not testable because it doesn't make unambiguous predictions in the first place. So gradually in the last 20 years, it has dawned upon the scientific community on, whoa, we're missing something serious here. Of course, it has been very difficult to find a way around it, to eliminate, so to speak, these other universes, to really rethink cosmology. And this is the theory that I propose in my book and that Stephen and I developed over the years is, I would say, one of the first fully blown attempts to really solve this problem.
We talked about...
And it's a very surprising solution too. No one expected this. It's a bit of a detective story, you see. I mean, we didn't know where we would end up. It would make a good film.
We started off our conversation talking about Stephen Hawking's book, A Brief History of Time. This is published in 1988. It becomes one of the best-selling scientific books of all time. I remember in the early 90s when I was in school reading it. And I can't say I fully understood it. I've never been good at math and physics and really science, and it'll become apparent in our conversation, Professor. But still, reading it was impactful. I remember specifically during the summer reading it, and at night I'd go out and just look at the stars and the moon and think about what the universe is, and you can still find this book.
I think that was the biggest thing about that book, indeed, and it made, one could almost say, it made humanity think about its place in the grand scheme. And this is also how I have known Hawking. And also, if you look in detail at his scientific research, even going back to the young Hawking in the 60s, it's very clear that his technical research, which is very difficult to understand for the layman, it is driven by these fundamental human questions that we all ask, like where do we ultimately come from? How does the whole thing hang together? And so Stephen was one of these rare scientists, I think, who was genuinely driven by the big questions, a humanist in the modern sense of the world, I would say, or in the modern sense of the word, I would say, yeah.
The book has a huge impact. You can still find it today in the bookstores, and yet he would come to reject the idea, some of the big ideas he put in that book, or some of them.
Yeah. Well, this is how science moves forward. So one of the highlights of A Brief History of Time was that in the middle somewhere, Stephen proposed what was in fact the very first mathematical model of the Big Bang, like the real origin, the origin of time. So this is a giant breakthrough. Physics normally deals with the evolution of systems from one state to another, and here was a theory which purported to describe the creation of a system, the origin of the universe. But then gradually it became clear that the model that Hawking had put forward in A Brief History of Time, out of his creation moment came an empty universe, a universe without stars, without galaxies, and therefore without life. And so we started to look for a better theory. And Stephen too, in fact, it's a testimony to his passion for understanding that he was able to move beyond A Brief History of Time. So it's the way science works.
And
we progress, we deepen our understanding.
And we start to see traces of what you finally get to in The Origin of Time, that we're going to dive into here in a moment, in his previous book, his last book, The Great Design.
Yes. The Great Design, I would say, sits somewhere in between my book and the vision and the theory that's Hawking finally arrived at, and Brief History of Time. And so it sort of floats somewhere in between. I think the biggest change between the young Hawking of the Hawking of A Brief History of Time and the later Hawking is that in A Brief History of Time, Hawking was trying to find a sort of ultimate causal explanation for why this universe. He was trying to study the cosmos from as if we are outside, from some sort of God's eye perspective. He was trying to find the ultimate theory, a sort of an objective, eternal truth hovering above and beyond the universe. And that all ultimately led to these paradoxes of the multiverse. Even the multiverse is an extreme version of this idea where you put yourself not just outside our universe, but outside the multiverse. And so we try to reconstruct cosmology, if you wish, from the inside out by taking more of an observer's perspective, which is of course the real perspective. We are within the universe and we look up and out and we try to understand it. And by developing this, we were ultimately driven towards what I would say is a more Darwinian-like of understanding of the earliest phases of the evolution of the universe, an understanding in which in the earliest stages of cosmological expansion, even the laws of physics begin to co-evolve, with the universe that is taking shape. And so if you take that reasoning further and you descend into the Big Bang, the picture that we arrive at is that the Big Bang is not just an explosion. It is even not just the origin of time. No, it's the origin of physics, of the notion of physical laws. So we arrive at some sort of Darwinian understanding of that primeval phase of cosmic evolution, which is very different from saying there is some sort of eternal external truth governing it all.
So it's not that there's the Big Bang and then suddenly all these laws of physics are in place. It's a process that's very similar, as you said, you referenced to biology. The name of your book is The Origin of Time. Has, I think, several different meanings to it. One of them is sort of a play on Charles Darwin's book, The Origin of Species.
That's exactly right. Yes. Of course, it's a variation of Darwin's title. In fact, you could say, and that the reason is, of course, that we, in a qualitative, general way, we take these general Darwinian principles all the way down into the level of physics. And so in the end, rather than coming to a sort of kernel of understanding that is like an eternal truth, we arrive at a fundamentally evolutionary understanding of the world around us.
So when we say a Darwinian aspect to this, we're not talking about the survival of the best laws or even the survival of the universes, since I guess we're rejecting the idea of a multi-universe. I'll let you explain.
Yes. So what is the analog, you could say, between variation and selection that we all know from Darwin, right? The analog would be the following. It's all happening into this early quantum phase of the universe, where quantum randomness, quantum theory is a theory of probabilities, is a natural source of randomness. So that's a natural sort of variation. But what is the selection aspect? Because there's no, as you say, what is the analog of the survival of the fittest? In fact, in this primitive environment of the earlier universe, the different species of particles and the different forces, they're interacting with one another as well. There is a kind of primitive environment which acts as through its interactions, which acts as a selection principle. So it's in fact the universe itself which is playing the environment.
So the physical laws develop over time.
Right. In the very first fraction of the expansion. So now you might say, well, wait a minute. If we only have this for a small fraction, there's another thing about Darwinian evolution. Usually we need a lot of time for selection to act, but we don't have a lot of time in the early universe. In fact, the laws of physics, as we know them, they sort of crystallized a fraction of a second into the expansion. But when you're forging laws of physics, it is not so much the length of time that matters, the duration of the process. It is the range of energies that your system traverses, which is the driving force, which plays the role of time in biology, which is the driving force for this process of through which the tree of laws, if you wish, forms to act. And the range of energies in the early universe is huge. It's stupendously huge, of course.
Evolutionary biology continues to evolve. Evolution continues onward. Does that happen with physical laws, or does it crystallize and now just remains that way? The laws of our universe are the laws of our universe.
Yeah. Yes. So we have no evidence. So we have no evidence that this change continues, but it's a very good question. In general, of course, I should stress that this whole picture that we arrived at with Hawking, it's a grand hypothesis, a little bit like Darwin's hypothesis at the time, but we don't have a lot of fossil evidence. Just like Darwin at the time, we don't have a lot of fossil evidence of this early phase of the Big Bang, of this, as you say, of this evolutionary character of the laws, which are now, for as far as we can see, fixed and crystallized. And that's why we think of the laws as eternal truths. So I see the 21st century really, and sort of the discovery of the observation of, say, gravitational waves and all that. I see that century as maybe we can unlock this earliest phase of evolution, this deepest layer of evolution, and find evidence for this hypothesis. One evidence, of course, one piece of evidence would be what you say. Maybe we can find traces, small traces of so-called constants of nature that change, or any other aspect of the physical laws that change. I'm not sure. Yeah, if I knew, of course, I would go look for it, but I'm not sure what would be the best way to find those. And also, of course, another aspect, and I think maybe this is also behind your question, if the laws of evolution if the laws of physics are also the result of a primeval evolution, then we should probably conclude, and this is also what all theories are saying, that they're not going to be eternal in the future. Even though, of course, when we cosmologists talk about time scales, it's ridiculously long. We are talking about easily billions of years. But the idea of eternal, that something is eternal, I very much doubt it.
Life is an important part of the book that you have written on the origin of time, Stephen Hawking's final theory. Life in the sense of trying to figure out how life fits in this universe.
Right. That's a whole chapter on its own. So our universe, down at the level of physics, down at the level of the laws of physics, down at the level of the particles we have and the forces, it seems almost perfect for life to be possible. In many ways, physics is the forces, the composition of the universe, the matter in the universe, the fact that it doesn't expand too fast. It's all perfect. If you change any of those properties of the laws of physics, often you get a universe without life. And in fact, this was one of the motivations that in the 90s, where we talked about, that led people to think about the multiverse. Because the laws of physics have those properties which seem so perfect that it almost looks like our Big Bang was sort of designed, that our Big Bang was just perfect for life billions of years later to become possible. And of course, that is very strange. So people said, oh, wait a minute, maybe there is not a single Big Bang, maybe there are many Big Bangs, maybe there is no design, maybe most of the universes are lifeless, but once in a while, you're bound to find a good one, a one which is habitable. That led to all these paradoxes, and now this final theory of that we put forward in this book gives a new answer to this question about life and how our existence relates to the nature of the universe around us. And the answer is fundamentally evolutionary. The design was not there at the start, but it is the result of an evolution of its own, and it's one which can only be understood retrospectively. In retrospect, by looking backwards, by reconstructing from the existing laws of physics how they came about. It is very much like the way Darwin understood the design, right? If you take the tree of life, Darwin did not try to predict the tree of life from the very first life form. No, he looked around, mapped out the fossils, and reconstructed the tree of life, and observed that the apparent design of the eye or of the brain or whatever is the result of a co-evolution from primitive forms.
It's really interesting to think about. Oftentimes we hear how remarkable it is that Earth had all these conditions just right to be able to have life. And then, of course, you can expand that. Well, you also had to have appropriate conditions for the galaxy, the Milky Way, the solar system. But if you really think it all the way through, conditions had to be right all the way from the beginning with the laws of nature that would develop.
Exactly. It's more, so when I talk about, indeed, in my book about the biophilic universe, I mean exactly what you say. Thinking it all the way through and observing that even at the level of the physics, there seems to be just a perfect fit. Of course, maybe we should point out the fact that at the level of the physics, it all seems perfect, does not mean that the universe is full of life, that aliens are all around, right? Because in between the level of physics and then having advanced life forms are many, many more evolutionary stages, and there may well be a bottleneck here or there.
What does that mean about design, do you think, when it comes to this? I mean, does life form, and maybe we're getting into philosophy, and it's worth talking about, I guess, philosophy, because I know this is something you talked to Stephen Hawking about. Does life form by chance that these things occur, or is it by design? And of course, when we say design, we immediately start to think of sort of a religious design. But again, Stephen Hawking's last book was called The Grand Design.
Right. Yeah, I don't.
Did that make any sense?
Sorry?
Did that make any sense?
No. I see. I was trying to think. I was trying to think why Stephen Hawking's last book was called The Grand Design, and I think, in fact, it was arguing there isn't a grand design, but then at the same time, it was kind of holding on to this multiverse idea, and so I think that's why I was saying earlier, at the time of writing of that book, my impression is that he was sort of sitting on the fence, neither committing neither to a design nor to no design. Of course, I mean, you can think of design as a religious connotation, but cosmologists and physicists and people like Albert Einstein and also the early Hawking thought they would find a root cause of the apparent design of the world around us in the mathematics underpinning the laws of physics. So they thought of a design in scientific terms, if you wish, as a kind of foundation rooted in the mathematical formulation of the laws of physics on which all the other levels of evolution could build. That's also the reason why Einstein and also Hawking in A Brief History of Time associate the final theory of everything with the mind of God. Of course, a God much like Spinoza's God, sort of as a grand architect, not a personal God.
No, that nature is God. That nature is God.
Yes, exactly. Yeah. And so that the design, that the mathematical kernel of nature is sort of the expression of God's design. Yeah. But the picture we arrived at is completely different. If we're in our hypothesis where the laws of evolution are where the laws of physics are not ontologically different from any law of biology, just a little more general, but not fundamentally different, one is almost forced to conclude that there is no foundation, that there is a certain finitude associated with our human condition within this universe. And that, I think you're right, that is more of a philosophical point.
You would have conversations with Stephen Hawking about whether this is philosophy or not.
Yeah, but he would always object that he would, when what I just told you, he would claim this is not philosophy. We are just trying to interpret our equations. That's what he would say. Yeah, so he claimed that was just science.
What does it mean when we say origin of time? And if we talk about the beginning of physical laws akin to how we have the beginning of biological laws, of course, we're always asking, how did the biological laws begin? How did life begin? To you, is that the same question as to how does the physical laws begin?
Not exactly. Maybe conceptually, yes, in the sense that also this is a famous phase of abiogenesis, sort of the emergence through complex chemistry of the first life forms. Even that phase of evolution has probably a lot of randomness and accidents involved, and the exact structure of, say, DNA, on which every other layer of life would be based, could have been different, could have turned out differently. So also there you have these same general principles that the explicit design is an emergent phenomenon and is not pre-programmed at the lower level of, say, chemistry or physics. What makes it, of course, extremely difficult to imagine, I'm now taking these same principles down the level of physics, but in contrast with biology or with chemistry, if we are taking these down to the level of physics, we don't have a layer, we don't have a deeper layer. And that's what makes it almost unimaginable, isn't it? We can always say, okay, biology is an emergent phenomenon, but it emerges from some reality before that, namely the physical and the chemical reality and the astrophysical reality. And this is difficult to get your head around, because we are sort of saying that the Big Bang, the ultimate origin, the origin of time, does not quite have a cause. And in a sense, if you don't have time, you can't really have a cause. So the two go together. But I would argue that since the discovery of this idea of a Big Bang more than 90 years ago, physicists have always tried to avoid taking this as a real origin. We've always tried to find our way around it. Maybe there is something before the Big Bang, maybe there is a bigger universe, maybe there is a mathematical truth above and beyond the Big Bang. I'm proposing something radically different. I'm proposing that we should take this idea of evolution, this Darwinian idea, and its implication that there is a real origin. The crux of our hypothesis is that we should take this seriously.
Is it impossible to know that about time before time? And I understand the contradiction in that question, the time before time. But could it be even impossible because it's just so outside our realm of existence to have something before time?
That is, I can only agree with that. Yes. And I don't I don't object to, and maybe this is behind your question a bit. So this is a hypothesis in which we're trying to practice cosmology, the study of the universe as a whole, by taking in a sense our human condition within this universe in account in our physical theory. And so maybe you're saying, okay, and so then we are driven to this evolutionary picture. And in a sense, the finitude that we are led to is related to taking that human condition in account. So you could say, well, maybe this is some sort of limit of what we can know and what we can't know related to our perspective. I can agree with that. Quantum theory, which is what this is all based on, is a strange theory. It's a theory which is counterintuitive, okay, but it's a theory which tells us both what we can know, but it also tells us a lot what we can't know. We can't know, for instance, the position and the velocity of a particle at the same time. So it's a strange theory. It poses limits of what we can talk about almost, and that's what I find is at play here when we construct our model of the Big Bang using these quantum principles. It is, for instance, all these other universes. Where did the multiverse go? You can ask. In our theory, it's just gone from the equations. It's as if we can't know this, and our theory knows, and our theory incorporates this. It's kind of fascinating, yeah. The last word on this has not been said.
Some people are going to be devastated by the idea that there is no multiverse.
Devastated, really?
Well, I think some people are into it. I know some of my friends are very much into the idea of there being a multiverse. And I think a lot of people still hold on to that idea that there's a multiverse. You said at the beginning of our conversation that one of the things you admired deeply about Stephen Hawking was he didn't get stuck on just with his 1988 book, The Brief History of Time, but his ideas would change over time as he kept doing the research. In the history of science, is that unusual, or is it common for a scientist to come up with a big grand idea and then they stick to that idea and defend that idea because they're attached to it?
You have examples of both instances in the community of scientists and cosmologists that I am familiar with. I've always felt a large openness, and that is the heart of science, really, right? To question one's ideas. It's really how you progress. Stephen, of course, was attached to his theory, but his passion for understanding, for advancing, was even greater. That's essentially what was happening, right? When he told me, and this was in 2002, I think, that Brief History of Time, that he now thought he was wrong. It wasn't. This was in a private conversation. It wasn't such a big deal. We were already onto something better. We felt we were already onto the next stage. You see, and that's really how these interactions worked.
Stephen Hawking lived decades with ALS, which is a degenerative disease. We all know who Stephen Hawking is. You, over the 2 decades you worked with him, the way you two communicated evolved as well. And you mentioned earlier for work on what you wrote in this book, The Origin of Time, the communication you had with him was really just through a few very gestures of the eyes?
Towards the end, yes. Necessarily so. I mean, he was able to write a few words now and then. But sure, yeah, there was it was very difficult towards the end. Yes, yes. It was only because we had developed that common language, and that included all sorts of tricks, of course, sign language and facial expressions, and the whole set of the whole toolbox that we could continue. So it became almost a fairly intimate affair, because we really had to be very close to each other and very concentrated, but very beautiful, because we were really, by the end of his life, onto something new, as I'm trying to explain in my book, and this was very exciting for both of us. Yes.
Would it be that you would come to him with ideas, and he would sort of give you an indication of yes or no?
Yes.
Yeah, that makes sense.
Yeah. And then and also I was trying to extract his ideas, which was more difficult, of course.
How'd you do that?
Yeah. Well, I sort of knew. I sort of had an idea, of course, of what his position was. So I tried to refine that position by probing him with questions and detecting. I could detect various levels of yes and various levels of no by the end, and so you could sort of proceed that way. Yeah.
Thomas Hertog has been our guest. Again, Thomas Hertog is an internationally renowned cosmologist. For many years, he was a close collaborator of the late Stephen Hawking. He's a professor of theoretical physics at the University of Leuven, where he studies the quantum nature of the Big Bang, and he is the author of the book that we have been in conversation about, On the Origin of Time, Stephen Hawking's Final Theory. Thomas Hertog, I've enjoyed our conversation very much, and I thank you for taking this time to talk to us.
Thank you very much. I enjoyed it.